hari ni saya ada banyak benda mau cover, so I suggest that you have your module ready, your pencil or pen ready to menyalin banyak-banyak. Okay, so today we're going to talk about this next subtopic which is called electromagnetic induction. Okay, and when we talk about electromagnetic induction, the single most important thing that we must remember is that we have to remember that this is different from the first subtopic. In the first subtopic, we look at how two magnetic fields, when two magnetic fields interact with one another, okay, they will produce a force. Okay, so according to the Fleming's left-hand rule, the magnetic field from the permanent magnet, okay, and the magnetic field from the current carrying conductor. So any conductor, okay, any wire will give you a magnetic field as long as there's current flowing through it. Okay, so permanent magnet plus the magnetic field from the temporary magnet, okay, the current carrying conductor punya magnet will produce a force. Okay, and that is the basic, that is the basis behind all the motor lah. Okay, contohnya kita punya fan. Okay, anything that requires motion, anything that requires force, motor lah. Okay, especially that is in the first subtopic. But in this next subtopic, we're going to look at the same things, two magnetic fields and a force. Okay, but we're going to look at it from a different perspective. Okay, and the perspective is called electromagnetic induction. Dalam bahasa Melayu, induction is arohan. Okay, arohan. Okay, arohan electromagnet. So if the English induction pun kau susah mau faham, apalagi kalau yang BM, apa itu teraruh itu? Apa maksud arohan? Okay, so we will come to that in a little while. Okay, but bear this in mind, that is entirely different from the first subtopic. Okay, and so these are all aspects of electromagnetic induction that we're going to look at. Okay, you have a magnet going into the solenoid, you have something that looks very familiar, but slightly different. Notice that there's no power supply here. Okay, in the past, when we were doing motor, there has to be a power supply because the current is the one that, helps to create the force. Okay, and one of the biggest applications of electromagnetic induction is the generator. Okay, the motor's function is to produce a movement, but the generator's function, apa fungsi generator? Okay, the generator's function is to produce current. Very different from the first one. Motor is to produce movement. Dia guna current untuk menghasilkan pergerakan. Okay, but electromagnetic induction is the other way around. Dia menghasilkan current. Okay, dengan menggunakan apa? That's what we're going to see today. Okay, so the first thing we need to know is to describe electromagnetic induction in a straight wire and in a solenoid. Two different situations. Okay, let me warn you once again that today's lesson is going to be quite fast. Okay, saya takut yang kamu tidak sempat salin. So if you cannot catch up on the salin, okay, just salin as much as you can, then you watch this video again bila kamu habis kelas nanti lah. Okay, so we have to look at the two situations again. Straight wire, okay, straight wire and a solenoid. Solenoid is a wire that dia kena lilit sampai, okay, like this. So straight wire and a solenoid. So one of the uses okay, of electromagnetic induction is our friend the dynamo. Okay, so the dynamo can light up the light when it is rotated by the tires. Okay, so so this is a dynamo over here. Okay, ini dynamo yang kita biasanya lihat pada basikal, and the dynamo can only light up the light as long as the person is pedaling. The moment the person stops pedaling, then the light doesn't shine anymore. Okay, so we find that when the conductor is moved in a magnetic field, current is produced. Okay, this is the main line of this. When the conductor is moved in a magnetic field, okay, current is produced. The production of current in the conductor by magnetic induction is called electromagnetic induction. Okay, seems a bit confusing when you read it at first. Don't worry, this is the main thing we want to understand today. Okay, and that's what we're going to talk about. One of the biggest uses of electromagnetic induction, as I said just now, is the production or the generation of electricity. How do we get our electricity? Okay, is by electromagnetic induction. In the past, kamu belajar, okay, hydroelectric dam, okay, menghasilkan tenaga elektrik. But did you ever stop to ask, macam mana itu pergerakan air itu? Macam mana itu air yang mengalir boleh menghasilkan tenaga elektrik? Did you ever stop to ask that? Okay, or penjana kuasa biogesim, okay, biomass, okay, dia bakar, bahkan, and then terus ada current. Okay, did you ever stop to ask how is it possible? How did the burning of this material suddenly produce current? Did it just happen like magic like that? Okay, of course not lah. Okay, it happens by electromagnetic induction, which is what we're going to learn today. Okay, so electromagnetic induction, this is where you can start to salin, but let me tell you, it's very a lot lah. Electromagnetic induction is the production of current when there is a change in magnetic field. Okay, so this is the syarat. Okay, arus akan terhasil, current akan terhasil lah when there is a change in magnetic field. Okay, now the change in magnetic field, okay, can happen in three ways. Okay, I'm sorry guys, there's not enough room for you to salin this. Yeah, this whole slide is yang kamu perlu salin lah. But if you don't want, you can just take a screenshot nanti you can salin nanti lah. Okay, so the change in the magnetic field can happen in three ways. Number one, you cut the magnetic field. Okay, when you cut the magnetic field means there is a relative motion between the conductor and the magnet. Means kamu punya wire, okay, dengan kamu punya magnet, okay, ada pergerakan di antara mereka yang menyebabkan pemotongan, there is a cut in the magnetic field. Pemotongan medan magnet. We know that a permanent magnet, sorry. Okay, fine, north-south. We know that the permanent magnet, there is an invisible line, okay, that goes from north to south, okay? But let's say if I take a conductor and I cut that invisible line, okay, that is what this means. When I cut the magnetic field, okay, there is going to be a current produced. Pretty amazing. Okay, it's like magic, you know. Okay, tiada-tiada benda yang di sana yang kamu nampak, tapi tiba-tiba kau buat begini, terus ada current mengalir. Okay, so that is the first way that we produce a change in magnetic field. Okay, the permanent magnetic field, we cut. Okay, we make a movement there lah. Okay, using a wire, okay, and the magnet. Secondly, you change the direction of the magnetic field. For example, this is north, this is south. Okay, we know that north, the magnetic field is from north go to south. Okay, sorry, I don't even know whether, okay, from north go to south. Okay, we know that. But if I change the magnetic field, I make this become north and I make this become south, the magnetic field is going to berubah arah. And it's from here to here, now it's going to go from here to here. So when there's a change in the magnetic field, okay, when you change the polarities of the magnet, how we do that nanti kita bincang, okay, how we do that nanti kita bincang. Okay, that is also going to produce a current. Okay, third way is the magnitude of the magnetic field change. Okay, first you use a weak magnet, then you make the magnetic field become stronger. How you make the magnetic field become stronger? You add more magnets. There are many ways lah. Okay, you change the value of the magnetic field. Okay, and that's how these are three ways that you can produce a current by electromagnetic induction. All of which, the most important one, okay, the most important one is the first one. Okay? The first one is probably the most important way. When there is a relative motion between the conductor and the magnet, okay, when a conductor cuts, okay, the magnetic field, okay, there is going to be current produced. Asalnya wire ini kan, asalnya this wire, tiada current ni mengalir ni. Okay, it's just a normal wire. But when you put a wire into a magnetic field and it cuts, okay, you have to move the wire lah, obviously. Kalau kau letak di sana saja tiada, there is no motion. There has to be a motion. Okay, kamu potong lah itu medan magnet. We cannot see the medan magnet, I know, but I need you to imagine that it's there. Okay, you've learned this since the first subtopic. Memang akan ada. Okay, north, south, memang akan ada. Okay, so you take a current, you take a conductor and you cut. Okay, and you will get the current produced. So the change in direction and magnitude of a magnetic field, okay, which is number 2 and number 3, okay, can be produced by using an alternating current, which use AC. Okay, AC, and we will talk about this in a little while. Okay, so this one, the change the direction and change the magnetic field, okay, we do it by using alternating current. Okay, this whole slide is this entire subtopic in a nutshell. Ini adalah rumusan bagi keseluruhan subtopic ini. Okay, so which is why I'm spending a very long time here lah. We are going to look a lot at number 1. Okay, and nanti kita akan lihat number 2 and number 3 also. But I want you to bear this in mind, that there has to be a movement, a motion, okay, in order to produce a current. Dulu, in the first subtopic is, kita guna current untuk menghasilkan pergerakan. We use current to produce a motion, to produce a force. Now, we are using force to produce a current. Okay, still in the same magnetic field. So it's totally terbalik daripada the first subtopic. Alright, so let's get this idea lah. So let's say you have a pair of magnets. Okay, this magnet here, magnet lah. Okay, and you hold a conductor. This is a conductor. Okay, a copper rod is a conductor. Okay, and the conductor is disambung kepada this thing called the galvanometer. Okay, let me tell you about the galvanometer. Galvanometer shows you two things. Okay, it's different from an ammeter. Okay, ammeter, kalau ammeter dia punya macam ni kan, dia punya jarum dia akan bermula dari kosong di sini. And then it will move here according to how much current there is flowing lah. Berhabis saya bergerak-bergerak and then I realized that I turned off my camera. Gosh, I'm such a narcissist. Okay, so this ammeter, okay, it starts from 0. But galvanometer, it starts at the center. Okay, it starts at the center. Of course, here is 0, sini adalah 1, 2, 3. Here is also 1, 2, 3, and so on and so forth. So it has a potential to either move to the left or to the right, depending on the direction of the current. Okay, now the galvanometer always points towards, listen very carefully, this one, this is something that probably may shock you a little bit. Galvanometer always points towards the direction where the current is coming in. Okay, listen galvanometer always akan terpesong, okay, kepada arah di mana arus itu sedang memasukinya. So for example, okay, if the current is flowing here, okay, the galvanometer is going to terpesong ke sini. Okay, let's say for example ini adalah arus mengalir lah kan. Galvanometer dia hanya adalah penunjuk arah. Okay, it's just telling you where is the current coming from. Okay, where is the current coming from? Very, very, very important thing. A lot of people get confused with this galvanometer. They think that, oh, kalau arus mengalir sini kan mesti galvanometer pun ikut sama. Tidak. Okay, totally not. Galvanometer shows you the direction where the current is coming in from. Dia datang dari mana. Okay, if the current is flowing here, like this, the galvanometer is going to move to this side. Okay, here. To show you that, oh, okay, current is coming in from this kepala, from this terminal. Okay, and at the same time, it's also going to tell you how much current, asal ada nombor-nombor di sini. So let's say, for example, okay, this is the 0, and let's say dia terpesong ke kanan, here, okay, sorry. That means you know that it's about 2 amperes lah. Okay, 2 amperes of current that's coming from this side, okay, dari sebelah sini. Okay, so bear this in mind when we're talking about the reading of the galvanometer. Okay, galvanometer tells you two things. Dari mana arah arus itu, and secondly, how much is the current that is flowing. So dia memang sangat special lah berbanding dengan ammeter. Ammeter just tells you how much current is flowing, that's it. But it doesn't tell you which direction it's flowing. Okay, but the galvanometer very special. It tells you which direction and it also tells you how much. Okay, let's take a look at this video, everyone. There's a few videos here. It's pretty long, so yeah. Oh, sorry.
Current carrying wire produces a magnetic field in the region around the wire. when current flows in a wire wound round a soft iron core, and electromagnet is produced. We have just seen that electricity can produce magnetic effects or magnetism. Can magnetism produce electricity?
Can magnetism produce electricity? Can. Okay, precisely the topic we want to talk about today lah. Okay, kita guna magnet untuk menghasilkan arus. Sorry, is it okay? Still running.
Look at the galvanometer.
Look at the galvanometer. Huh?
What happens to the galvanometer pointer when the wire moves up and down across the magnetic field? The galvanometer pointer shows a deflection to the right when the wire moves down and a deflection in the opposite direction, that is, to the left, when the wire moves up. What does the deflection of the galvanometer pointer indicate?
Okay, deflection and galvanometer. Bila ada pesongan means what?
The deflection of the galvanometer pointer indicates that there is a current flow. As the wire moves up and down, the magnetic field lines or magnetic flux are being cut.
Okay, listen to that very carefully. When the wire moves up
As
and
the
down,
magnetic fluxes are being cut, an EMF is induced across the wire. This is known as electromagnetic induction. The induced EMF will cause a current to flow in the wire. This current is called the induced current.
okay, a few keywords that you're going to hear a lot in this subtopic. Number one is the word cutting of magnetic field lines. Okay, now the word magnetic field lines, okay, is also known as the word magnetic flux. Okay, this word lah. So depending on di mana kamu belajar ini lah. Most Americans, I think, Americans like to use the word flux. Okay, because kita dari British system kan, so we like to use the word magnetic field lines. So both of them mean the same thing. These magnetic field lines alias the flux, when you cut it, bila kamu potong the magnetic field lines, you are going to produce, okay, you are going to produce an EMF, an electromotive force. This is from the previous subtopic. Okay, you are actually producing an induced EMF, which then produces your induced current. Okay, so I'm going into a little bit of detail. Okay, which is the correct step lah. Biasanya orang akan lompat terus dari sini pergi sini bah. The cutting of the magnetic field lines will produce an induced current. That's it. Okay, but actually what happens is the cutting of the magnetic field lines will induce an EMF that will cause the current to flow. And this current is called the induced current. Okay, there is a mistake in this video. Sepatutnya bila dia mengalir sini kan, this one sepatutnya terpesong ke sini, tapi dia terpesong sebelah. Okay, we will talk about that reason another day lah. But the main point is this. The moment the galvanometer shows a deflection, bila dia terpesong, okay, that means that there is current flowing. Okay, that's the most important thing we need to know. Okay, and we know that there's current flowing because we are cutting the magnetic field lines. Okay, take a look at this video next.
What happens to the galvanometer pointer when the wire is stationary in the magnetic field?
Okay. So you notice that it's
The
in the magnetic
galvanometer
field.
pointer does not show any deflection, indicating that there is no current flow.
There's no current flow because
Why?
there is no what? There is no movement. There is no relative
The
motion.
magnetic flux is not being cut by the
The
wire.
magnetic flux is not being
Thus,
cut.
no EMF is induced. Hence, there is no flow of induced current.
Okay, so even if you put it inside, but you don't move it, okay, there's no current. there has to be a movement, there has to be a cutting of the imaginary magnetic field lines. Mesti dia terpotong, baru akan terhasil arus. If you put it inside and you put it in for a long time, there will still be no current flow. Okay, because syarat untuk induced current, syarat untuk induced current, okay, is the cutting of the magnetic field lines, the cutting of the magnetic flux. Mesti terpotong. Bukan potong dan stay di sana saja. Kalau kau potong stay di sana, the galvanometer will terpesong and come back to zero. Because your wire has stopped moving. Okay, your conductor must keep moving in order to produce the current. Okay, another video, sorry. Banyak apa tu video ni? Oh, sorry. Hey, apa ini? Hey. Oh, there.
What do you think may happen to the galvanometer pointer when the wire moves parallel to the magnetic field?
Okay, wire moves parallel to the magnetic field means
the galvanometer pointer does not show any deflection, indicating that there is no current flow. Why?
Okay, this is a good question that we can answer a little bit later.
When the wire moves parallel to the magnetic field,
no
magnetic flux is being cut.
No magnetic flux
no
is being
EMF is induced. Thus, there is no induced current flowing in the circuit.
Okay, so most important thing is that even if you put it in, there's no current. Even if you move, but the movement is the same direction as the magnetic field lines. Doesn't this sound familiar? The movement is the same direction as the magnetic field lines. There will be no current. Just like Fleming's left-hand rule. If the current and the magnetic field are in the same line, there will be no force. Okay, but in this case, if the movement, okay, and the magnetic field are in the same line, there will be no current. Okay. One more, sorry.
What will happen to the galvanometer pointer if the wire is made stationary, but the magnets are moved upwards and downwards as shown?
You'll find that the galvanometer dia terpesong. Kan? Walaupun wire
the
tidak bergerak.
galvanometer pointer shows a deflection to the right when the magnets move upwards and a deflection in the opposite direction, that is, to the left, when the magnets move downwards. Why?
Why? Very important.
As the magnets move up and down, the magnetic flux is being cut by the wire. An EMF will be induced across the wire and cause an induced current to flow.
Okay.
An EMF is induced across a conductor when the magnetic flux is being cut by the conductor. This is known as electromagnetic induction. The induced EMF will cause an induced current to flow in a complete circuit.
Okay, so the most important thing is that in both situations, the first situation, magnet tidak bergerak but the wire is moving. Second situation, the wire tidak bergerak but the magnet is moving. Okay, in both situations, the same thing is happening. There is a cutting, you're going to hear this word a lot, cutting of magnetic field lines. The main prerequisite, syarat paling utama untuk electromagnetic induction for an induced EMF is there must be a cutting of the magnetic field lines. No cut, no current. Basically, that's it. No cut, no cut. No matter what you do, no, you must cut it. You don't move the wire, but you move the magnet, cut. You don't move the magnet, but you move the wire, cut. You moved both the magnet and the wire, obviously they're cut lah, kan? Don't need to think about it lah. But if you move and then you stop, cut for a while only, and then totally no current. So tell me, is there a deflection on the galvanometer if the wire, if this copper, this one is held stationary? Obviously there is no deflection. Okay. Now, this one, I'm going to explain a little while later, but basically when you move it up, when you move this one upwards, okay, it's going to deflect to the left. The galvanometer is going to go towards the left. There is a mistake in the video just now, but I want you to hold on to the fact again. Galvanometer always points to the direction where the current is coming in. So since the current is coming in here, it will deflect to the left. Okay, when this one is going down, okay, if I move this down, the galvanometer will deflect to the right. Okay, when it is moving sideways, okay, sideways means, you know, kau move sideways like this, okay, parallel to the magnetic field lines, there will be no deflection. Okay, and if you move with a higher speed, let's say kau macam tu saja kan, dengan kamu macam tu kan, okay, what you're going to happen is the one, the one with the bigger movement, okay, you're going to get a bigger deflection. Okay, and this is the basic of electromagnetic induction. So what happens to the galvanometer pointer when the wire moves up and down across the magnetic field? Okay, the key word is over here, the galvanometer pointer will deflect. Okay, deflect in bahasa Melayu is dia akan terpesong. Okay, secondly, what does the deflection of the galvanometer pointer indicate? Dia terpesong. So what does it mean? It means that there is current flow. Okay, and okay, so this is the one. How is an induced current produced? Okay, when a straight wire moves and cuts the magnetic field lines or the magnetic flux. This is how an induced current is produced. Inilah cara arus dihasilkan dengan memotong flux magnet. You take the wire, you cut the magnetic field, and there will be current flowing in the wire. And that's how our electricity is made. Okay, you think what? Air mengalir terus ada current, please. Okay, they actually move a magnet or a wire. Okay, number 4, what happens to the galvanometer pointer when the wire is stationary in the magnetic field? Obviously, there will be no deflection because there is no cutting of magnetic field. Okay, they are parallel. If the movement and the magnetic field is in the same direction, we consider it as no cutting of magnetic field. Okay, what will happen to the galvanometer pointer when the wire moves parallel to the magnetic field? Same thing. Okay, no deflection because there is no cutting of the magnetic field, no cutting of the magnetic flux, therefore no induced current. Okay, so syarat untuk induced current, you must cut in a not parallel way lah. Okay, kau cut sengit macam ni, kau cut sengit macam ni, kau cut macam ni, okay, directly perpendicular, definitely akan ada induced current. Okay, number 6, what will happen to the galvanometer pointer if the wire is made stationary? Wire itu tidak bergerak, but the magnets are moved upwards and downwards. Okay, the galvanometer will deflect. Dia akan terbergerak. Okay, there is a cutting of the magnetic field because of the movement of the magnet. So again, syaratnya hanya satu saja. Doesn't matter which one you move. The most important thing is the magnetic field must be cut. Okay, so in order to produce a deflection in the galvanometer. So relate the motion of the copper rod that produces a current in it to the direction of the magnetic field lines. The movement of the copper rod must be perpendicular, okay, to the direction of the magnetic field lines. Very important thing. Dia tidak boleh parallel. Okay, it must be perpendicular. Especially if you want to produce a big current, okay, you want to make sure that the wire is cutting it perpendicularly lah. Okay, now this is the first situation yang berkaitan dengan just one single conductor. Okay, but we also have to look at electromagnetic induction by another thing which is called a solenoid. Okay, so a solenoid is basically a wire, okay, or long wire yang kau kasih gulung. Okay, and then what you do is you either put the magnet into the solenoid or you push the solenoid into the magnet. Okay, depending on that. So there is that motion over there lah. Okay, and we're going to find that, oh, okay, when you do that, there is going to be an induced current. Okay, take a look at this next video. Banyak ni video. Okay, because it's such an important subtopic.
So I have an ammeter here
This is the maximum volume,
and
sorry.
two coils. This coil has 100 turns, and this coil has 25 turns. I will first connect the 100 turn coil to the ammeter.
Okay, so if you didn't hear just now, the first coil, the first solenoid has 100 turns. Dia ada 100 lilitan and the other one has 25. Okay? 25 lilitan saja. Take a look at the galvanometer, guys. Here.
I am now going to take the magnet, and notice as I move it towards the coil, I get a pulse of current in the positive direction, and when I pull it out, there's a pulse in the minus direction. And notice if I just hold the magnet there, there's no current flow. It's only when the magnet's moving and when there's therefore a change in magnetic flux with respect to time inside the coil. If I move the magnet slowly, I get a small current. And if I move it quickly, I get a larger current. Okay, so it's the rate of change of magnetic flux inside the coil that determines how much current is flowing. And we see that I can get about 10 microamps if I try to move the magnet very quickly. Okay, so now let me connect the...
Okay, so you find out that this is a slightly different situation. Actually, almost the same. Okay, remember the situation just now where there is one what do you call it? One conductor and the magnet, and you're moving the magnet, the conductor yang stay still. Okay, but instead of the conductor now, you have a coil, a very long wire yang ada banyak coil. Okay, so essentially, because there are so many coils, there's going to be a lot of wires. Okay, there's going to be a lot of wires that are going to be cutting the magnetic field lines at the same time. Okay, when you put the magnet in, when you put the magnet in, okay, all these wires over here, okay, are going to cut the magnetic field lines. Okay, and that also produces a much bigger, definitely much bigger induced current compared to kalau dia just one single wire. Okay, one single wire can produce, but very small. But if you have one wire that is, dilingkarkan, so you have many small wires, then when you put the magnet inside, okay, it's going to cut all these wires. Okay, it's going to produce a definitely much bigger induced current. Okay, so same thing. When you push the bar magnet into the solenoid, okay, there will be a deflection in the galvanometer. Okay, the first thing we need to know is whether it deflects or not. Okay, nanti kita akan bincang tentang arah, how to determine the direction. Secondly, you hold the bar magnet stationary in the solenoid. Think about the situation just now. There will be no deflection. Why? Because there's no cutting on the magnetic field lines. And you pull the bar magnet out, okay, like this. There will be a deflection, but in the opposite direction. So bila kamu kasih masuk, tengok bila dia masuk, dia pergi kanan. Ini bila dia tarik keluar, dia pergi kiri. Okay, masuk, back to zero, kanan, kiri, back to zero. Masuk, back to zero, kanan, okay, and things like that. So you hold the bar magnet stationary, you push the solenoid towards the bar, same thing, there will be a deflection. Hold the bar magnet stationary in the solenoid, no deflection. And finally, you pull the solenoid away from the bar magnet, there will be a deflection. So the same thing, like just now, the conductor and one magnet. You move the conductor, deflection. You move the magnet, deflection. Okay, but now you have the magnet and the solenoid. Okay, you move the conductor, okay, deflection. You move the solenoid, okay, also deflection. Okay, so what is the deflection of the galvanometer, okay, with the magnet and solenoid coming closer to each other? Okay, it will deflect to one particular direction. Okay, we will talk about the direction. I think we have time. We may talk about the direction today, but we'll see how. What is the deflection of the galvanometer with the magnet and the solenoid moving further from each other? Okay, it will deflect to the opposite direction. So you put the magnet in, deflect one direction. You pull it out, it will deflect the other direction. Ada arus, okay, tetapi dia akan bertukar arah. Okay, so this is the one. Explain how the induced current is produced in a solenoid using a magnet. The key word is there is a relative motion between the solenoid and the magnet that makes the magnetic flux to be cut. Okay, so the relative motion, okay, between the solenoid and the magnet. Relative motion means pergerakan relatif. Means they are moving lah. Okay, antara solenoid dengan magnet ni dua-dua adalah salah satu atau dua-dua adalah bergerak, and pergerakan ini menyebabkan the cutting of the magnetic flux. We have not run away from what I have spoken since the beginning. Okay, induced current is produced when there is a changing or cutting of magnetic flux. Asalkan itu berlaku, akan terhasil arus. Just that there are many situations in which this can happen. Okay, so for example, like this, you push the magnet in, it's going to produce a current. Okay, push the magnet in, it's going to produce a current. You pull the magnet, okay, and of course, different situations will call for different things. So when a bar magnet is moved towards or away from the solenoid, the turns of the solenoid, okay, will cut the magnetic field line. So imagine the magnetic field from the north over here. Okay, it's this, so all these wires are going to cut the magnetic field. And when they cut the magnetic field, it's going to produce an EMF. Okay, and EMF is induced across the solenoid. So a complete circuit is formed when the ends of the solenoid are connected to a galvanometer. The induced electromotive force, EMF, will produce an induced current in the circuit, and galvanometer shows a deflection. So, as I said just now, cutting of magnetic flux induces an EMF. Ini akan menghasilkan satu induced current. Okay, the three-step process. Cutting of magnetic field lines induces an EMF, produce an induced current. Okay, EMF dan current adalah benda berlainan. Okay, that is from the previous chapter. Number 4, what happens to the galvanometer pointer when the magnet remains stationary in a solenoid? Question you need to ask, is there a movement or not? Kau kasih masuk tapi kau kasih stop. Is there a movement? Of course, there is no movement. No movement means no deflection. Okay, there is no deflection because there is no relative motion. Okay, so when we talk about relative motion, okay, we are talking about magnet and solenoid. Okay, this is a case-specific kind of reasoning lah. Okay, bila kita cakap pasal solenoid dan magnet, kita usually talk about we talk about relative motion. You can also say it does not deflect because there is no magnetic field lines being cut. There is no cutting of magnetic flux. Also can. Okay, it's the same reason. Okay, why there is no induced current. Okay, here's another video. There's a lot of videos today.
One induced current is produced when a wire is moved cutting the magnetic field lines of a magnet. Actually, this is not the only way to produce an induced current. If the wire in the form of a coil of many turnings is fixed, and the magnet moves towards the coil, this will also produce an induced current. Reversing the motion of the magnet by taking it out of the coil will produce an induced current in the opposite direction. This phenomenon can be explained like the previous case, as the wire of the coil cuts the magnetic field lines of the magnet. But a more scientific and more general explanation must be discussed. Now we need to know the reason why moving a magnet towards a wire can cause an induced current. Remember, in the first part, our case was a moving wire with a magnet in place. This process produced an induced current, which is explained as follows. The metallic conductor wire cuts the magnetic field lines of the magnet, causing an induced current in the wire. But now in part 2, the magnet is the moving part, while the wire in the form of a coil is the fixed part. And this also can be explained the same way. The metallic conductor wire cuts the magnetic field lines of the magnet, causing an induced current in the wire. But here we can have a more scientific and wider explanation. that prepares us to have more advanced applications. For this case, we can say that the metallic conductor wire is exposed and affected by a changing magnetic field. You can also say a variable magnetic field, causing an induced current in the wire.
Oh, okay. Sorry. Okay, so the main point is this lah. The video is kind of like a summary. Okay.
But induced current is produced.
Oh, okay, sorry. So let's go back to this. So state two ways. Okay, two ways to produce an induced current in a conductor. Number one is a straight wire moves and cuts the magnetic flux. Okay, number two, there is a relative motion between the magnet and the solenoid. Sorry, I should have split this into two. Okay, so cara pertama, you have a straight wire, just one piece of wire, and you cut the magnetic flux. Secondly, there is a relative motion between the magnet and the solenoid, which is this case lah. Okay, there is a relative. So both of these ways produce induced current. Okay, why does the galvanometer pointer deflect? Because the induced current flows. Okay, so all this explanation is to just explain to you macam mana arus boleh terhasil. Okay, dua cara lah. You have a straight wire, you cut the magnetic flux. Secondly, you have a magnet and a solenoid, and you either move it in or you move it out. Okay, so the relative motion produces an induced EMF, which produces an induced current. So in conclusion, okay, so you have a straight wire that is moved in a magnetic field. Okay, the straight wire cuts the magnetic field lines and induced current is produced in the wire. Okay, secondly, you have a bar magnet that is moved inside a solenoid. Okay, there is a relative motion between the magnet and the solenoid. Ada pergerakan relative. Okay, between the magnet and the solenoid, and this causes the cutting of the magnetic field, which produces an induced current. Or there is a change in the magnetic field. Okay, you can say it both ways lah, either this or this. Okay, both these explanations are acceptable. Relative motion produces a change in magnetic field, but whatever it is, there is a magnetic field cut, and the magnetic field cut will produce an induced current. Okay, if after today's one, yeah, I know this subtopic we have to go even slower than we did with the first subtopic, because there's a lot of things that we need to understand over here. A lot of new words, okay, words that we've never used before. Relative motion, cutting of magnetic field lines, induced EMF, induced current. Okay, so that's why we have to take this, not to say as slow as you can, but we try and see lah. Okay, so an induced EMF, in conclusion, okay, still conclusion, an induced EMF is produced by the cutting of magnetic field lines when a magnet and a conductor move towards or away from each other. Okay, electromagnetic induction, this is the thing that we mentioned right at the beginning, is the production of an induced EMF in a conductor when there is a relative motion between the conductor and a magnetic field, or when the conductor is in a changing magnetic field. This is this is the definition. The proper definition of electromagnetic induction is this. Okay, penghasilan DGE arohan. Okay, production of induced EMF in a conductor when there is a relative motion. Apa syaratnya? Relative motion between conductor and magnetic field, or when the conductor is in a changing magnetic field. Okay, the actual definition for electromagnetic induction is this. So it's kind of a lot. Okay, there's a lot of things that we need to wrap our heads around. Okay, but again, as I said, the most important thing, I'm not sure whether this is a video. Is this a video? Oh, it is a video.
Gambar ini menunjukkan susunan radas yang menggunakan galvanometer berpusat sifar jenis gergelung gerak untuk mengesan arus arohan yang akan terhasil dalam ruang kubra. Biasanya galvanometer jenis ini tidak begitu peka dan mungkin tidak dapat mengesan arus arohan, ataupun pesongan jarum penunjuk galvanometer itu adalah sangat kecil. Galvanometer yang lebih peka ialah galvanometer alur cahaya. Galvanometer ini tidak mempunyai jarum penunjuk yang biasa. Penunjuknya ialah satu alur cahaya yang terdapat di dalam galvanometer itu. Dan alur cahaya itu akan membentuk satu imej cerah pada skrin galvanometer. Apabila arus dikesan oleh galvanometer tersebut, imej cerah itu akan dipesong sama ada ke kanan ataupun ke kiri, bergantung kepada arah arus yang melalui galvanometer. Sekarang perhatikan apakah yang berlaku kepada imej cerah apabila rod fulcrum itu digerakkan ke atas, kemudian digerakkan ke bawah, dan kemudian digerakkan ke atas dan ke bawah berulang kali. Perhatikan gerakan rod fulcrum dan juga pesongan imej cerah yang berfungsi sebagai penunjuk pada skrin galvanometer. Apabila imej cerah itu bergerak ke kiri atau ke kanan, itu menunjukkan bahawa arus dikesan oleh galvanometer. Dan arus itu ialah arus arohan dalam rod fulcrum. Perhatikan pesongan imej galvanometer. Dan juga perhatikan bahawa imej cerah akan dipesong hanya apabila rod fulcrum itu bergerak memotong flux magnet. Apabila rod fulcrum itu pegun, tiada arus arohan dihasilkan.
Okay, so that is kind of the introduction, baru introduction ni kan. Okay, that is the introduction, okay, to electromagnetic induction. Okay, there is a lot of things, there's a lot of things that's happening. There's a lot of things that will happen in this subtopic, and I don't think it's good to rush through this. Okay, as I've told you before, this is one of my most favorite chapters actually. I love this chapter a lot. But it needs to be learned for me Okay, it needs to be learned slowly You first need to get your head okay, you first need to get your head past the meaning of electromagnetic induction. Okay, what is the meaning of electromagnetic induction? How is the induced EMF or the induced current produced? Okay, there are two ways, okay, where the induced EMF or the induced current is produced. Okay, and then of course, third one is, what is the purpose of the galvanometer in this whole electromagnetic induction thing? Why do we not use an ammeter? Okay, because ammeter cannot show both directions. Ammeter can only show, actually ammeter doesn't show anything, it doesn't show any direction. It just tells us that there is current flow, there is no current flow. But galvanometer does two important things. It not only shows us how much current is flowing, is also showing us the direction where the current is flowing. Okay, so as an introduction to this subtopic, okay, you need to make sure that you understand this one first before we go into the next part, okay, which is the next class Okay, so understand what is electromagnetic induction, understand the two ways, okay, dua cara untuk menghasilkan arus arohan, two ways to produce an induced current. Okay, and number three, the function of the galvanometer, okay, in all these things. Okay, once you have this in mind, then you know that, okay, saya kena peka ni dengan perkataan-perkataan ini. When I say relative motion, when I say solenoid, okay, when I say induced current, when I say induced EMF, you need to make sure that these words sudah terbenam masuk dalam kepala dulu. Okay, that's why if you take a look at the module, I think saya baru 2 muka surat 1 jam 2 muka surat saja baru saya terbergerak. Okay, I cannot go too fast, because if I go too fast, it's just going to spin past your head. Okay, so take the day, everybody, take the day. Like if you want to watch this video again, I will send you the link later. But take some time to sit down and really understand now what is happening in this subtopic. Because after this, it's going to get very technical. Okay, after this, we're going to look at different laws. We're going to see how the direction of the current is determined. Okay, but in order for you to understand it, you need to understand how induced current is produced. Okay, so that's it for today. So the good news is there is no homework, but there is a responsibility to yourself. Okay, you are responsible to make sure that you yourself understand what is happening in this subtopic. Okay, I cannot force you to do that. Like, you have to do it yourself.